Hi, welcome to Hardwire Video. This particular video clip is going to cover the use of Hardwire when we're laying up parts and really looking at vacuum infusion. We will be doing another clip shortly on wet processes and resins that work well there. The first thing to talk about in Hardwire, we've already covered some of the basics about cutting, choosing your material. Basically, in laying up is where Hardwire really starts to shine. It's incredibly easy to lay up. It's very, very straight material. So most of the times where you're using unidirectional plies, you're on top of stringer caps in wind blade molds, where straightness is key. One of the other key things about it is, even if I do this, I can't wrinkle these fibers. One of the biggest problems with high modulus composite fibers are if they're not perfectly straight, if there's any wiggle at all in them, you don't realize the full potential. So in molding operations, that's especially important. It's a little less important in pultrusion, where you can back tension the material. But for the folks that are watching this video that mold, getting the fibers straight is everything. You paid a lot of money for them. We might as well have them straight, have them work hard. One of the most fundamental things about Hardwire is there's basically a 5-to-1 ratio on layups. So if I'm laying up a large wind blade or a large part, I can place one ply in the mold with Hardwire. If I was to compare that to a 25 ounce glass unidirectional, which I have over here, in the same time it took me to place 5 layers, or 1 layer of Hardwire, I have to place 5 layers of unidirectional. Also, you'll notice that a lot of these glass plies are actually, the fibers are somewhat wavy. It's just a natural part of the process. What that means is it's not only taking me longer to get it in the mold, but it's taking me, even when I get it in the mold, I'm not necessarily getting the properties that I was after. The other thing is you can notice here just the fluff factor between 1 layer of Hardwire and the 5 plies. Doesn't look like a big deal here on the tabletop, but when I'm placing 5 plies of Hardwire, that means I've got to place 25 plies of the glass, and it starts to get quite fluffy. Now the last thing to see, and I don't know if you can see this here with the camera as we hold it up, but I can see actually right through this Hardwire material. It's very, very permeable, which means once the layup's done, the resin's not only going to move along it, it's going to move through it much, much faster. You can see here with the glass, it's very impermeable. It's very difficult to drive resins through these materials, and if we use carbon's much worse. You also notice that I'm starting to get fiberglass all over my right hand because it's over here by the glass. It's starting to get all over me. By the end of the day, I'm going to have a good itch going on. One of the great things about Hardwire is it doesn't fray. You don't get glass all over yourself, and you end up going home at the end of the day just about as clean as when you came. The last thing is I'm going to take these 2 plies and just step on them for a second. This is one of the unique things about Hardwire. You'll notice that the glass ply started to pick up a lot of dirt. And I'm not sure if you can see that on camera, but their glass tends to pick up dirt. The Hardwire, for some reason, just doesn't want to pick up dirt. And even if it does, we can actually take and wipe this down with a solvent just to clean it up. So if you're out there cutting a bunch of plies, for some reason they fall on the floor, it does happen, you're going to end up with still clean plies with the Hardwire, dirty plies with the glass. Now laying up Hardwire is pretty straightforward. If we were going to do a 5-ply laminate, something that would be typical 1/4-inch laminate, it would actually equal a laminate that was 1.25 inches thick in glass. To lay it up is just quite simple. Place a couple plies on top. One of the things we do with Hardwire is sometimes in the laminates, depending on whether there's a cross ply or not, you can use a lower density Hardwire material. And typically what we tell folks is for ultimate properties, use the 23 wire per inch. For super fast infusibility, basically creating a layer that's going to move resin effectively through the laminate, use any of the wire densities ranging from 4 wires per inch all the way up to 16 wires per inch. You can see both of these. Obviously the 4 wire per inch material is very gappy. The 16 wire per inch material with low viscosity resins still moves resin very aggressively. In a second, we're going to go to an infusion where we're going to show you what those materials do live. When you're using core materials, Hardwire works just like glass. It works just like carbon, where you can simply make beautiful cord panels by placing a layer of hardwire down, putting the core against it, and placing additional layers of hardwire on top in multiple directions if you like. One of the unique things about this is the cores we ask you to use don't necessarily have to be microgrooved. The microgrooving does cost a bit more in Divinycell or balsa. Just a scored core to let the resin from one surface to the other through works just great. And let's take you one step further, some of the things that Hardwire eliminates. I'm sure many of our viewers are familiar with the scrimp systems. It's a place I had some past history. And basically with scrimp, what we are going to encourage you, our material will work wonderfully in any vacuum infusion system. If you're using a patented system, you have to have a license for that. We'd recommend that you contact the parties that have those. But basically with scrimp, you have all these extra materials. You have to have a peel ply involved, distribution media, so there's quite a bit of resin that ends up getting thrown away, and then these nifty feeder channels that we have here at Hardwire. So basically when you're scrimping, you can scrimp Hardwire, it will work beautifully. But the key is all of this stuff takes quite a bit of time and money to put inside a mold. You owe royalties on it. With Hardwire, the material is so permeable, all you have to do is feed it any way you can think of. There are several techniques for feeding laminates through springs or this type of omega tubing. But the beauty of Hardwire is, even though our system is patented, we have a patented process on using it in molded construction, what we don't require is a license for using that particular process. What we're going to show you next are a couple little tricks. I just want to show you one last thing. If we have this high density material, one of the neatest ways to create preferred feeder channels. Let's say we've run out of this omega tube, we just don't have any, we're going to have to find an easy way to feed the laminate. One neat way to do it is you can create your own kind of Hot Wheels track feeder channels just by grabbing a small group of wire and pulling them away from the fabric. You can tell, like, when we cross ply that, basically we have a nice big channel for the resin to go through. So it's an easy way to create quick and dirty ways to get resin to move through the laminate. One of the biggest things that all of this means is, when we sum it all up at the end of the day, making money in the molding business, a place where I have very strong roots, basically boils down to getting the reinforcement in the mold quickly, and 1 ply versus 5 plies versus 25 is going to make a tremendous difference just getting the material in the mold. Second, because the Hardwire is so much more permeable, and again, you kind of get a nice look through this, that it's extremely permeable material in all kinds of different densities. It means that the resin is going to flush through this material 10 to 100 times faster than it would in a glass or carbon laminate. And in carbon, it is very dramatic. Faster resin infusion means a shorter gel time. Shorter gel times result in more accurate gel times. Usually the longer a gel time is, the more difficult it is to maintain that gel time accurately. And then finally, quicker gel times mean faster peak exotherm. Usually the temperature will rise more quickly. And then there's always the cool down factor. So when you add all that up, a lot of these advantages end up being squared or cubed in terms of mold turnover. What we're finding is customers using Hardwire can easily turn large parts in a molded system over in a single shift, whereas in glass or carbon, just the long layup time, we're talking about hours for infusion for very large wind blade parts, and then of course hours longer for the peak exotherm and demold time. Those kinds of dramatic time increases can save our fabricators, the Hardwire fabricators, tons of time and money. Last, let's just talk about the thermal conductivity of Hardwire. And one of the beauties of this material is it is thermally conductive. If you have an application that needs good insulation, this may not be your material. But for guys building large parts, things like railroad cars, bridge decks, wind blades, that thermal conductivity can mean a lot. And I'll tell you how. Usually once parts are infused, some people use heated molds. If you have a heated mold, sometimes a mold made out of this material, it means you're going to be able to conduct the heat into the part much quicker. With pultrusion, it's all about heat transfer and getting heat into your thicker parts through your die system. This material will conduct heat substantially faster than glass will. Last, for the wind blade builders, guys building tapered parts, what's so dramatic about Hardwire is in tapered parts where you have thick sections followed by thin sections down further in the blade, you can use chemistries that are very, very hot in Hardwire that you couldn't get away with in glass. In glass, you usually get a peak exotherm or a runaway exotherm in the thick section, while very little of that heat or energy is transferred to the thin section. So part of the part's too hot, part of the part's too cold. With Hardwire, the beauty is it's so thermally conductive that if the thick section is heating up, the wires act to transfer that heat down to the thinner section in the mold, and you end up with a very, very even temperature profile, which results in a nice even cure, lower thermal stresses, and again, faster cycle time. Now we're going to switch you over to our little infusion race, where you're going to get to see this dramatic improvement in fusibility. We'll also show you the scrimp system, and again, I'd like to let you know that if you are using scrimp, you do have to buy a license, and you should contact that outfit to do that. Let's switch over now. Hi, welcome back to our two-part series here on laying up Hardwire and infusing it. The hum you hear in the background are the vacuum pumps. We're going to get you to our layup in a second. I wanted to just, for you all to take note that the resin we're using today is a Hetron resin. It's Hetron 942-35. It's a low styrene resin from Ashland. They were nice enough to send it over for the test. And it's a great crew of people over there, not to give them too big a plug, but they are doing a great job for us working on high adhesion resins specifically for Hardwire. There's going to be a whole other video clip on resins and fiber finishes of Hardwire for high adhesion composites, but just wanted to mention our good friends at Ashland helped make this possible. Now, as we said in our first part of our series, we were laying up Hardwire, and today what we're going to do is just show you in Infusion the dramatic differences that you can experience. First off, I can just talk about laying up the panels. Most of this side of the table is Hardwire, in fact all of it. You see glass on top. We almost always include a glass ply on top of the layup, and what that gives us is basically a glass surface that acts to protect the Hardwire. So almost in all cases, include a glass ply on top. Just walking through these real quickly, this particular panel on the far edge will probably be the slowest of the Hardwire infusions. It's 2 plies of uni, maximum density, 1 ply of 16 wire per inch material to act basically as the way that the resin will be flying through the material, and then 2 more plies of this high density material. These 2 panels are really our favorites, and they really are kind of the Hardwire used in its best engineered state. You could consider them maybe panels that you would see inside a mega yacht or a very large structure where you're not looking to pack massive unis in there like you would in a wind blade, but basically something where you have a high density skin followed by several cross plies of low density material to act literally as a resin core, followed again by another high density skin. All these panels are going to be shown at IBEX, so you'll be able to actually see the panels at the IBEX show if you're there in the year 2003. Notice that we have included some glass on the outside edges as you look at the panels again. One of the things that's really tough about Hardwire is it is tough to cut once it's post-infused. If you have a water jet cutter, it cuts beautifully, but what we recommend is anytime you're trying to show the product off, put it in a boat hull, put it in any kind of molded part, at the trim edges, leave all glass. Try not to cut into the Hardwire. Trust me, that'll be some of the best advice we give you in this video. Cutting Hardwire is difficult. It takes a very high torque water-cooled diamond bandsaw or a very high torque water-cooled circular saw like a high torque concrete saw, or a water jet cutter, and I can't overstress how important it would be. If you have a lot of cutting to do, use water jet. On this side of the table, we're basically going to have our Hardwire competitors, and you'll get a real good idea of some of the things that make Hardwire so great. First off, although we couldn't show it all to you because it took quite a bit of time, the Hardwire panels took us about 15 minutes to lay up. The panels on this side of the table took us more than an hour, and they really demonstrate some of the things that are difficult about laying up composites. First, the carbon panel, the black panel here. This panel will probably be trash when we're done with this race. You noticed on the Hardwire side there was no resin infusion media. Basically, our feeder channels were plugged directly into the Hardwire. There are we're not violating anyone's patent. We have a patent on this ourselves, but you can plug the feeds directly into the Hardwire with no other distribution media. As we move back over here to the carbon, what you'll see is we've done exactly the same thing. Now, if you want to make good parts, we don't recommend doing this, but it will show the dramatic difference between the two materials. In laying up the carbon, I can tell you that cutting it out was difficult because it constantly frayed and created a real black mess around here. It got all over us. It was incredibly itchy. And at the end, I don't know if you can see this in the light, but you see these waves? Okay, this is the beginning of wrinkles. Not only are the fibers somewhat wavy by virtue of the stitching, but these waves, these are the wrinkles. These are the things that really, really kill the composite properties when we're all done. Essentially, resin that doesn't have distribution media is only going to flow, gosh, I think in here we're probably only going to get to about here before the resin kicks off. So in carbon, maybe 5 or 6 inches without a resin feed. In Hardwire, you're going to be able to go 48 inches or greater without separate feeds. So anyway, here's the carbon panel. You can see the wrinkles in the fiber. You can see the waviness. And again, as I push on this, maybe you can see that. The thicker the laminate, when it's under vacuum, you can actually dent the laminate. That denting, in a big part, where you're walking on it sometimes to make sure the bag doesn't have any leaks, that denting causes further wrinkling in the preform. It can be a real problem. Let's move over to the glass panel. The glass panel, and all these are the same thickness panels. The glass panel is a glass uni panel, again with no feeds on there at all. And essentially there's 10 layers of glass here just to get to the same 1/4 inch that we had with the Hardwire. What's important is this panel, if the resin was to move through it, would actually act like a noodle compared to the ultra-high stiffness of the Hardwire. Again, all glass. We're probably only going to get the resin to here. The rest of this is actually going to be trash. I'm going to move you over to our final panel. We needed to make one good glass panel to use as a comparison. This basically is set up in a scrimp-like fashion. It's not actually scrimp. It's a good show of a patent that McDonnell Douglas has where we're shooting from one side to the other. But it does show the use of distribution media and feeders. This is all the material that we're going to be throwing away at the end. You notice with the Hardwire, basically nothing gets thrown away at the end. All this material is extra. It costs extra. It takes extra time to lay up. It's a bunch of stuff that really the Hardwire has eliminated, both in things you need to stock and pay for, and of course it's going to really eliminate the trash. For the guys that do resin infusion for a living, I mean the big guys, the guys that are really doing millions of pounds of this stuff, you can ask any one of them and their trash bill is astronomical because of all this throwaway material. With the Hardwire, you throw away next to nothing, and that's really the key, is whatever you pay for, you want it in your part. So with that, let's get this race off and start it. We're going to go ahead and catalyze the resin. We're just adding the MEK catalyst to a pre-promoted Ashland vinyl ester here, the Hetron. Typically, we had to set the gel time to give it a nice even race here. We set the gel time relatively long. What you'll see is when you're using Hardwire, you can set the gel time, what you're used to setting in Infusion, maybe hours. Suddenly you're going to be setting it to 10 minutes because the parts infuse so quickly. George is now going to place all the feed tubes in the bucket. And in just a second here, you're going to see basically the two sides feed aggressively, and you'll get the race will be on. So hopefully we'll be able to see that. You'll actually see these panels turn gold with the Hardwire inside. This glass panel will just turn relatively clear. Try to get a nice even start here to the two, and they're off. actually both feeding at roughly the same pace here. We have a little bit of a leak we want to address right there. Just try to make it an even race. Okay, you can see the panels filling. You can see the distribution media moving relatively quickly, where it's moving across the top of the laminate. One of the difficulties here with this particular laminate is it moves across the top, but then it has to move through the thickness, and you actually get quite a gradient of flow. You can see that the all-glass laminate, the resin's not moving at all. I mean, it's just kind of dead stuck. And just to make sure you realize, this tool is actually heated. This tool's up around 100 degrees, so we're getting a really good, should get as good a flow as you can get. You notice that the carbon laminate, we haven't even been able to get any resin into it. Carbon under vacuum is extremely difficult to infuse. And meanwhile, you can see that the Hardwire laminates are beginning to fill pretty aggressively from the inside out. This is where the laminate itself acts like acts as the distribution media. Just going to let you watch this process for a bit. One of the things that you're seeing here is as our distribution media panel fills, let's just take a swing back over to the other side, just again to give you a rough idea. I want to swing back. You can see we're filling here. We haven't made it anywhere in the carbon panel, and believe it or not, there's not a piece of plastic in there holding that back. In our glass panel, we've moved about, gosh, a couple of inches. Maybe an inch at the most. And you can see actually the resin infusion starting to go a little bit bad here, starting to run up into the wrinkles. This is what happens when resin infusion goes too slow. Things go wrong. Resin begins to run in wrinkles, it creates islands, they create dry spots. The slower infusion goes, the lower the permeability, the bigger the problem. Here in our scrimp panel, we have moved across the top of the panel in the distribution media, but we're starting to run out of steam, a little bit of steam. If you were to monitor the infusion flow, you'd actually see it moving very quickly over the top, but slowly through the thickness in this high-density panel. What that can lead to is at the end something called a waterfall effect, where it actually falls over the back of the panel, leaving a big dry spot on the inside. Back here in the Hardwire panels, you can just see a nice, even progression of the resin moving all by itself. What's important here is the resin is moving in a straight flow front. It's basically wetting out from the inside out, and what that means is as it moves very carefully and across, you'll have a very uniform flow front. Things can't really go wrong because you're not trying to dump resin over the top of the panel. You're moving it along the panel and through the thickness as you go. You can see that the Hardwire now showing up from underneath the glass. One of the things that's gone, this is actually the first time we've set up this test. We wanted to make sure we filmed it, because it does take some time to set up. One of the surprises in this is actually that the most densely packed unis on the far side, that's actually the maximum amount of unis, are actually moving just as quickly, just slightly slower than some of the panels that have more cross plies or more areas for the resin to flow. So that's a bit of a surprise even for me. Love to see that kind of fast flow though. Over here in our race, we'll just take one more quick look here. You can see we're almost done on our Hardwire panels. You notice that the vacuum infusion in the scrimped panel, or the scrimp-like panel, is really starting to lose steam. Okay, we're slowing down, and you'll see like in a vacuum infused panel, you can't go much more than 36 inches. This is a full 36 inches of flow. We put in an extra feeder, although we're not using that right now, just because we need this for a test panel. So we had to make sure that we had ample flow in there to make this thing go. These other panels, though, really show things going horribly astray. You can see the difference between the glass is wetting out some. We're getting more wet out because of the wrinkle in the bag actually transferring some of the resin. You can see it kind of gurgling through there. Again, creating a spot here, a dry spot. What that's going to relate in a large part, that would really be a problem. That would be causing you enormous problems. And you can imagine the gel time to get the resin from here to here, it would take days. There's no way it would get there. In the carbon part, again, it is never ceases to amaze me. When you take carbon fiber with vinyl ester resin, it acts almost like a sheet of plastic. The fibers are so small in the carbon, they're just teeny. As they nest together, they create tighter and tighter and tighter packing density, which would be great if you could get resin through it. The problem is you just can't get the resin through it. We haven't even moved a quarter inch into the carbon panel. I believe here we've moved maybe about 2 inches at most into the glass panel. And coming back to the hardwire panels, boy, that was good timing. Basically, we're done. At this point, this resin could be gelling. You can see this panel is all turned the pretty silver color, kind of a silver gold coming through the dark resin. The higher density unis, they are not moving quite as fast, but the beauty is these panels are essentially done. We could begin the cure right now. I'm not exactly sure how long that was, but it was essentially less than 10 minutes we were able to flow 36 inches. If this was a bigger boat, remember, 10 minutes we flow 36 inches. On a large structure, as long as you put your feeders every 36 inches, that same 10 minutes, you could be doing giant boat hulls, giant wind blades, all kinds of great big structures. Again, if we had a highly heated tool, we could kick the heat in, the heat would transfer, we'd begin the cure. I'm going to come back over one more time to our scrimp panel now that these are finished. And I just want to show you, this is what we really see when scrimp runs out of gas. In infusion media, because it is so impermeable, combined with the glass, now we're really starting to slow down to the point we might have to fire up a second feeder, which is more tubing, more wasted resin. Again, I need this as a test panel, so we're going to have to get that one going. And you can see we can fire it back up, but it requires just requires a whole nother feed of resin. Yeah, you can see right now, because we're sucking in a new line of resin, is that that's all, it's coming, it's all pulling in. Just in the time that we've emptied, opened that up, at this point, because there's some styrene in the lines, we're actually sucking some air into the panel. These are some of the things that go wrong with some of these other systems, is that because you have to have multiple feeds, you have distribution media, all kinds of things, these little bubbles that are boiling through the panel right now, these are basically things that are going to cause us quality problems. Again, I want to take you back one more time, and we'll probably stop this video before it gets too boring. But basically, our glass panel, we've moved, 2.5 inches. You can see just on the sides of the laminate where we may have a little bit of less pressure in the bag, we're beginning to move up the sides of the panel. So we're beginning to form an island. Okay, if this wrinkle were to come up and come back around, we could actually island that part off. Huge quality problem. And one of the issues is in a wind blade, that could be an awfully expensive quality problem. The carbon panel, actually much to our surprise, this is a good thing. We're going to be able to save this carbon. We're going to be able to pop it back out of here, do this again. We'll probably use the same carbon. We'll just trim off this last quarter inch. I mean, it has not moved into the carbon panel at all. It's almost as if we had put a piece of plastic here on this feeder tube. Just never ceases to amaze me. And then just coming back over to the hardwire panels, you can see, but basically they're done. We'd be ready to cure these. These would be all over, and we'd be ready to demold very quickly. So, in summary, the material is amazing at moving resin. You can put your feeders directly on the material with no distribution media, no peel ply, and no patent violations. And with the high heat transfer, we're going to get an even cure. And it's just very, very easy even to stop the resin because we have high permeability. We can put a bleeder in that has very low permeability. It's just amazing. I mentioned the wrinkles in the carbon fiber. One of the amazing things about this, even if I walk on it or push on it, I can't get it to wrinkle. The material is just impossible to wrinkle. And even if you use Hardwire just as an internal call plate, a way to get the wrinkles out of your glass or carbon, it's amazing for that. But when used by itself, you create very straight, very stiff, perfect composites, which is really what you've set out to do. Basically, that should sum it up. The micro rebar of Hardwire, high resonant fusion speeds, the itchy, scratchy, dirty, fly-generating carbon fiber, glass, low infusion rates, or you're buying patents from someone. That really sums up what Hardwire is all about. Thank you for watching.